strength evaluation of concrete floors with specific reference to post-tensioning. What is your takeaway from this presentation? Reasons for strength evaluation. It is not an uncommon situation. Underlying concepts of strength evaluation methods of concrete floors. A brief overview of common procedures. Background to yield line method of strength evaluation, which is the core of this presentation. Step-by-step instructions of how to carry out a yield line analysis method, followed by detailed examples of RC and post-tension floors using yield line analysis method to determine the load carrying capacity. It is not uncommon that the capacity of an existing floor, such as the one on the right, needs to be re-established, evaluated. There could be change in occupancy, which means change in loading. Observed damages to the building, which raise doubts regarding its strength. There are established procedures to determine the strength of existing floors. Now, the schemes commonly used are progressively more complex. That means you start with a simple method. If it doesn't work, you go to the next method, which is a little bit more involved. If it doesn't work, then you go to the next, and so on. These schemes are, the first one is strip method, which is typically used in original design. And if the strip method doesn't work, you go to its extension, which is a moment redistribution. After that, finite element analysis using the right program can give you a better distribution of load and identify the demand. Yield line comes next if the finite element doesn't work. Finite element is based on the elastic solution. Now I take the opportunity to mention that. And the yield line is post-elastic. And if yield line doesn't work, the ultimate is load test. Yield line analysis is the penultimate method of strength evaluation prior to engaging in the expensive and more complex, laborious load test. Now let us see whether that can go out of the way. Good. Good. So step number one in strength evaluation is the strip method. The strip method is most probably the method originally used for the design of a floor such as shown on the right. Summary and evaluation of the strip method leads to the capacity of the floor, and if the computed capacity in any strip, you break this into strips, falls short of demand, then you go to the next step. Here in these three images at the bottom, the one on the left shows a breakdown of the slab in your first evaluation into strips in up-down direction. The image in the middle gives you the strips in left, right. You have to have strips in orthogonal directions, and then you show the post-tensioning, and you go and calculate the strength. If it doesn't work, then you come and try to take advantage of the post-elastic response. Pre-stressing steel and strands, when pulled, can stretch substantially beyond their initial elastic limit. If this is the elastic limit, they can stretch far beyond the limited stretch of elastic. This is conventionally rebar, and this is post-tensioning. This deformation without increase in resistance can be utilized in redistributing the force to places where resistance is available. The diagram on the left is typically idealized like what I am showing on the right. There will be elastic response followed by a straight line, which is the post-elastic. That is, or that was for a bar when you pull. The same applies to bending moment. A section that is under bending will deform initially in the elastic regime shown here, and then once it reaches its ultimate elastic limit, it will deform with essentially the same bending moment. This is the simplified diagram that we use in the analysis. The locations where this phenomenon is likely to occur is typically at midspans or at the face of support. These are the locations where the demand is usually higher than elsewhere in the member. So the ACI code permits, if the conditions are right, by conditions are right, that means if you have enough reinforcement, to have the calculated elastic moment. This red line is what we normally obtain in our analysis. Our analysis is based on elastic response. To have this raised or lowered by a certain percentage, could be as much as 20%, and readjust the bending moment to see whether the elastically calculated demand can fall within the hatched region. For example, on the right, if this is the face of the support on the left and right, the elastic solution which comes out of your strip method is shown in red. You are permitted to raise the bending moment or lower it within a certain percentage of this magnitude, and the percentage is limited typically to 20%. When obviously you raise the bending moment here, you have to do so for the entire span. You raise the bending moment of the entire span or lower the entire span to see whether it meets the demand. Now, this post-elastic distribution is very important for post-tensioning, and I am going to explain why. Look at this diagram on the left. The top shows a typical distribution of moment. Below shows the reinforcement positioned according to this moment diagram if this were conventionally reinforced. Where you have a negative moment at the top, you put reinforcement at the top, and where you have moment at the bottom, you put reinforcement at the bottom. Everywhere you have a bending moment, you require reinforcement for the safety of the member. Now, this, when we contrast to post-tensioning, doesn't apply. In post-tensioned members, shown on the top right, you have typically a tendon which goes from one end to the other. Presence of this tendon results in availability of capacity, positive and negative. The hatched region is the capacity based on the presence of post-tensioning. Your demand moment from applied load, typically, like shown on the top left, is higher at the top, lower at the bottom. Here I have 2M and I have 1M. So when you match the demand, which I have shown here, over the capacity which is hatched, invariably you end up with over capacity. So it works well if you pull the dotted red line down. You have the option. So if the demand exceeds the capacity here by a certain amount, you can lower the demand to fall within the capacity, and that will meet the requirement. So the simple strip method gives this red and the black here. It doesn't typically have this option of doing the readjustment. The strip method, the commercially available program, has the ability that you can ask for distribution of moment to take advantage of this reserve at the bottom if the solution shows inadequate capacity. This is not available, as far as I know, in the commercially finite element programs yet. Then, if the previous method, which is redistribution, does not apply, then you model the entire floor using finite element analysis. You model the floor, put the post-tensioning in it, and you break it into subdivision of a mesh, and you obtain a distribution of which I am showing the contour of the deflection on the right. Now, why finite element than after the previous effort? Because finite element solution gives you a more relevant demand force in the structure than the strip method. The strip method does not include the option of the demand on one strip being shared by the strip next to it. So each strip is looked at independently in isolation. Finite element overcomes that restriction. So that would be your next step to see whether you can make sure that the structure is safe. Now, if the finite element doesn't work, then the next step is the yield line analysis, which is the focus of this presentation. The yield line analysis is based on the simplified concept I am showing on the right, that if you have a slab, you load it. Initially, you have a load deflection distribution like I show here, linear elastic. But when the location of maximum demand moment yields, you will have a load distribution and deformation like here. You have rotation taking place with no increase in load. This rotation with no increase in applied load will result in collapse of the member. So the member, in this case, the slab, can resist the load until there is a hinge forming at midspan, which results in folding of the slab into two. So increase of load results in formation of a hinge as shown in the diagram. At formation of the hinge line, the load deformation of the slab is shown by the straight line AB here. Deformation takes place but no increase in load. Under added load, the slab segments bounded by the hinge lines displace as solid plates with no increase in resistance. Slab collapse takes place through the rotation of the hinge and the solid body downward displacement of the articulated slab segments. Now, what do I mean by articulated slab segments? I mean there must be enough hinges so that the mechanism, the breakdown of the slab into segments will displace down and result in failure. The hinge line analysis is really the last analytical step in strength evaluation of the slab. Yield line analysis is based on the concept that at failure, concrete slabs break down into segments separated by lines along which the adjoining segments can rotate. In this case, for the configuration shown on the top right, the breakdown of the slab into segments shown below it will result in each of these segments rotating. This rotates about the support line there, and this triangle rotates about here, so the slab can collapse. So collapse occurs if adequate number of post-tension elastic hinges are formed and their rotations result in slab to fold down. Should yield line analysis does not lead to the required results, if the yield line analysis doesn't show adequate capacity, the last final step of the strength evaluation is load test. Here on the right is an image of a floor which was considered to be possibly inadequate. Hinge line didn't work out, and then we had to perform load test for it. When you want to load test this or any floor like I am showing at the top, you shore the floor that is going to be loaded in case it collapses, because the load you put is the ultimate factored load. It's not reduced load. It is the maximum load for which, under unusual circumstances, the floor is designed. This floor has to pass the factored load applied on it before it could be declared safe. So you shore it, obviously with some gap, and the shoring is continued a number of levels to make sure that the live load capacity of the levels below added together can sustain the self-weight and applied load of the floor you are going to test. You position dial gauges here and also dial gauges for the level below, since the application of the load may result in shortening of the columns and the downward movement of this slab also, albeit to a much lesser amount. ACI says apply the load in 4 steps. Here I have a quarter of the load on the top left, half of it, 3/4, and the entire load. And for each load, measure the displacement, wait until the slab is settled in its deformation, and unload back and forth 4 times. Here I have the load deformation of the slab we just looked at. Here is the first loading. You wait about 24 hours, you unload it, then you load it again, you unload it. After several load and unload, the residual deformation after removal of the load should be less than a certain amount. In other words, the recovery, the rebound for the subsequent cycles should be less than a certain percentage, so that the floor could be considered safe. Now we continue for the next. The concept is, I'm repeating the concept that we are going to follow right now for the yield line analysis. This is an image which we looked at earlier on in the presentation. If you have a member loaded with bending moment, initially you have this straight line, but once you reach a certain bending moment, then it is assumed that the deformation will be taking place, but there will be no gain in load. That is the concept explained here. The consequence of deforming without increase in resistance is the diversion of applied load to where resistance is available. It is argued that if the location of hinge formation cannot resist more load, if there is resistance available elsewhere in the structure, it will, and there's a path to it, the load will be diverted to that location. Redirection of the load is the core of ductility that forms the background to yield line analysis. Concrete slabs including post-tensioning, are viewed as ductile material, meaning once they reach their capacity, they have the ability to divert the increase in load demand to where resistance is available. Now, this simple illustration is intended to crystallize the concept before we go to the slab. In this example, I have intersecting beams supported at the far ends. The reinforcement in AB, is less than the reinforcement in CD. They look identical visually, but one of them has less reinforcement, and we apply a load at intersection and follow the response. The increasing force F is initially resisted by reinforcement in both of the intersecting beams. Displacement under the increasing load F initially distributes the demand equally between the two beams based on initially equal stiffness. With increase in force F, the bar with smaller reinforcement reaches its plastic moment capacity. Addition of load results in the load increments to be resisted by the bar with larger reinforcement, where capacity is available. This is the concept. Once this bar can no longer take the load, and there is another option which has capacity reserve, the other one kicks in and picks up the capacity in demand. The ability to continue to deform with essentially constant resisting moment in the weaker member and the available capacity in the stronger member to provide resistance is the underlying concept of the yield line theory for estimating a floor slab's capacity. Now, I want to illustrate that in a more familiar example, a cantilever. Let us consider this cantilever, propped cantilever at the end. Put reinforcement AS, put twice the reinforcement to AS, and apply a load in the middle. The load in the middle, 2AS over the top and AS at the span. The yield moment at the bottom is MP. Here the yield moment will be MP. But the yield moment at the support will be 2MP because it has 2 times the reinforcement. With increasing load, the member collapse is shown here. Using the collapse mechanism shown here, we can calculate the demand. Here, the moment resistance is MP. Here is 2MP. Structure breaks down, collapses. The geometry of the collapsed structure is straight line, rotation, rotation. This is the way things are assumed. The computation of the collapse load is based on the concept of conservation of energy. What does it mean? It means the work done by externally applied load in its displacement, which obviously is force times displacement, must be equal to the work of resisting internal forces in deformation of the structure. As the load comes down, work is done, and as the hinges rotate, work is done. The work done by the applied load must be equal to the work resisted or achieved by these hinges. The work of the externally applied load is force times its displacement. This force times its displacement. The work of internal resisting moment, the moments here and here, is the plastic moment of the location times rotation of the hinge. Moment times rotation is the work done. Now the rotation at C, the rotation here is this distance divided by this. Alpha is delta divided by L over 2. Yeah, alpha is delta divided by 0.5 L. Rotation at this point is 2 alpha. So we have the rotations. The work done with the external force is P, which is the force, times its displacement. P times displacement is the load. So internal work is plastic hinge times 1 rotation, plastic hinge at the midspan times its rotation is 3 MP alpha. Now external work was P times delta. Member capacity, by equating those two, member capacity is the load capacity is calculated to be this value. So this capacity is based on the yield line analysis of that propped cantilever. Now let us look at a slab. In this case, the slab is supported at the sides and loaded. Load deformation is shown at the bottom right. Increase in load results in hinge line shown here. At formation of the hinge line, the load deformation is shown at the bottom right. Under added load, the slab segments bounded by the hinge lines displace as solid plates. Here I like to repeat the word solid plates. Solid plates with no increase in curvature. We assume that they remain solid in the same formation. Slab collapse takes place through rotation of the hinge and the solid body downward displacement of the articulated slab segments. What we saw in the previous slide was the case of a slab supported on two sides, but if you have other configurations, such as the examples shown here, obviously the hinge formation will be different. These are several examples of hinge formation for slab supported in different configurations. The test carried out on square bottom left or rectangular bottom right confirm the assumption that I illustrated in the previous slide. If you have an irregular situation like the one on the left or on the right, the key is to assume the hinge lines such that they intersect at the common points if you have more than two hinge lines. In this case, you break each piece in subdivisions, in triangular parts. The hinge line is here, but this other line is just for the purpose of calculation. For calculation, it is easier to find or to know, or the centroid of the triangle. This is a triangle, so the work done by this segment will be its weight times displacement of its centroid. That is the reason it is subdivided into segments, triangles, for ease of calculation. The conservation of the energy for a uniformly distributed load is expressed like here. Load applied per unit area, that is the force or demand per square foot, times the area of the segment, times the displacement of the centroid of the segment, is equal to the moment of the hinges around the segment times the rotation of each. This is moment time rotation, is force times displacement. This is really all that it says. And the external work is obtained by taking the force times displacement, and the force being the area. For quadrilateral solid, you can break it into triangles as I described. For uniformly distributed loads, the centroid is easier to be calculated by taking the centroid of the triangles. Now, if you have concentrated loads, the work done by the concentrated load is the load times the displacement below the concentrated load. This has nothing to do with the centroid of the segment. It is displacement under the concentrated load. Now let us look at this example. For the internal work, you have the plastic moment of each of the hinges, in this case this hinges, times its rotation. If you have, now I'm going one step beyond into the nuts and bolts of calculation. We covered the concept. The concept was external work must be equal to internal work. But now when it comes to calculating the internal work, let us just pause for a second. You have the moment times rotation. The moment is the plastic moment, the capacity. If you look at the section I am showing you, like I showed you on the top right, it is conventionally reinforced. Typically, the reinforcement is either at the top or at the bottom. Mostly, there may be at both sides, but typically the larger reinforcement is at the top or at the bottom. The contribution of reinforcement is considered to be its yield stress times its cross-sectional area. If I want to calculate the capacity, each of these are assumed to have yielded, and they act at this arm to provide bending moment. So the tension in the bar will be its area times its yield. For conventionally reinforced slabs, the reinforcement is typically at the top or the bottom or both at the top and bottom. The arrangement of reinforcement simplifies the computation of moment capacity, since the geometry of the lever arm of the tension force for moment calculation is known. This is the arm of the moment. So the moment is area of the reinforcement times the arm times the force. There must be a force there too. Must be force times the arm. Now, for post-tension slabs, the tendons are typically at the top over the supports and at the bottom of the member around the midspan. Let us look at this image. Column supported. Tendon is high here, low here. Again, it is high here, low here. So if you have a hinge line that goes from the column to the center of slab, the intersection of a hinge line with tendon can occur between the high and low points. If the hinge line is here, the tendon is high here, the tendon is low here. So in this section, the location of tendon through the depth is not constant, it varies. It is necessary to detect the intersection of each tendon and each non-prestressed bar with the hinge surface. In each instance, the location of the tendon, amount, and the orientation of the reinforcement as it crosses the hinge line must be determined in order to account for its contribution in the hinge line moment capacity. Now, what it says, if you want to calculate the moment capacity, each of these tendons cross the section at a different height. In addition, they may cross the section not normal to the section. They may cross at an angle. The angle as well as the location come into the picture. That is, I don't want to say impossible. That is very difficult, very demanding on a design engineer to go through all that computation. But don't worry, the computer programs, commercially available programs, do that all in the background for you. All you have to do is put the mouse here and here draw a line. In the background, it calculates where intersections are, what is the orientation, how much is the force, what is the distance to the neutral axis, and what is the capacity. All you have to do is draw the line, and then you can read the capacity right away. So that is why the yield line analysis for post-tension members has become a practical proposition because of availability software that can do the job. In addition, computation should allow for the fact that tendons generally exit a hinge line at an angle. This is what we discussed. Now I want to give you some background in how this is done internally. You will not do this manually, so don't worry. Computers do it for you. I'm just reviewing with you what in the background takes place. For example, for the moment capacity of this segment, where this is the hinge line, this is the tip that comes down, work will be done along here and also along hinge line and along hinge line here. Along each hinge line there will be a moment and rotation. Here also there will be moment about the hinge line, which will have also a component parallel to this. And likewise here, there will be moment along the hinge line and it will have a component. So hinge line AB, this is the hinge line, and this is the segment which is segment that is deforming. Now the hinge line AB rotates about this axis AB because this point O displaces delta. That is why it rotates, and the entire triangle comes down with it. Rotation of hinge line AB, rotation of this is downward movement divided by this length. This is this one. Rotation of this hinge line is component of this rotation along this hinge line. So you have to multiply this, which you had before, times the cosine of this angle. So that is how it works. You have the rotation of the plate here. You have to multiply it by the cosine of this angle for one and the other angle for the other. So these are the rotations. These are the rotations. And if you have a quadrilateral, it will be somewhat similar. This will be a straight line, but these two will also rotate. Their amount of rotation depends on the rotation here and their orientation. And I have now, this is a trapezoid. Rotation is about here, and downward movement is here. The calculation for the rotation of each of these hinge lines is given in here. The load capacity is obtained from yield line analysis, is always a lower bound. This is an item to be aware of. What it says is that after you're done with your evaluation, you have to validate it. What does it mean to validate? The yield line capacity evaluation always gives a capacity less than the actual capacity. But you have to make sure that the capacity you calculate, even though it may be less than the required, but it is less than the value you calculate. It is more than required, because the being lower bound values means that the method overestimates the capacity of the member. Among the many possible envisaged collapse mechanisms, there is one which gives the load capacity correctly. This is the value to be used in design. In other words, the hinge assumption that you assume gives you a capacity. You assume a different hinge assumption, hinge pattern, it gives you a different capacity. Now you have to make sure that the pattern you have assumed has the lowest capacity, or it gives such a large reserve of capacity over demand that based on your judgment it is acceptable. In practice, to arrive at a reliable load-bearing capacity, the design must make sure that the solution obtained is the least capacity. Alternatively, and that is what is mostly used here, it must be ascertained that the solution obtained exceeds by far the target. In addition, changes in the assumed pattern do not result to significant decrease of the computed value. The computed value can be regarded as approximate but acceptable. Approximate but acceptable because it is overestimating the demand by such a large margin that changing in collapse mechanism by a small amount will not be resulting in significant demand, in significant capacity change. The validity of collapse mechanism assumed can be established by changing the configuration of the assumed mechanism slightly, or other features of the geometry, and repeating the computation. If the new collapse leads to a larger load capacity, it validates the original assumption as closer to the least capacity. Otherwise, the new configuration should be used as the basis of validation. The process must be repeated until a change in the configuration of the collapse mechanism leads to a higher computed load capacity. That means you're going the wrong direction. Now, with a computer program, all this is very fast because you just use the mouse and click at point A, click at point B, and that will, in the background, create a hinge line, and then the capacity is calculated in the background. In practice, if the computed load capacity for a credible hinge line exceeds the demand by a high margin, based on the engineer's judgment, the result can be considered acceptable. Now I want to go through a number of design examples. The image shown at the right is a case we had to evaluate. The post-tensioning is shown left to right, but after construction it was determined that rebar was not placed as shown on plan. So we had to calculate the capacity of this region based on the post-tensioning alone. This type of collapse mechanism was assumed. From here to here, deflecting downward. This triangle hinges about here, and then no downward movement here, no downward movement here. So the region was broken down into these segments. The analysis method the analysis resulted in load capacity by far exceeding the demand. So the selected mechanism and the outcome were considered acceptable because based on engineering judgment, this is critical, it was considered that this collapse mechanism is not unreasonable. That's important. That's a judgment call. And because the calculated capacity on this mechanism, for this mechanism by far exceeded the demand, the result was considered as acceptable. Now, in reality, this point could be a little bit more down or up, but the result was so much more that it was considered acceptable. This is another example showing the corner span of a roof construction, which was post-tensioned with tendons up down and also a band here. The objective of the evaluation was to determine whether the corner slab panel of the roof garden can safely sustain the planned landscaping, whether landscaping here can take place. It was designed as a simple roof. The post-tensioning, non-prestressed reinforcement, and other features of the roof slab are shown. Rebar and the post-tensioning. Construction drawings showed the arrangement of prestressing and non-prestressed reinforcement. Analysis such as redoing the strip method did not result in conclusive solution. So, using a software, commercially available software, this hinge line mechanism was assumed, center of the panel downward, hinge line along these two directions, and there will be no hinge lines around this perimeter support. For a small displacement delta at the centroid, for a small displacement delta here, these four segments move down and rotate about these lines. The following applies. The sum of the moments along the hinges times rotation must be equal to the applied load times its downward deformation. These are the parameters of this relationship. Sum of moment times rotation equal to the load times its displacement. The work done by each of the slab panels is the load on the sub-panel times the displacement of the center of gravity of it. For each panel, like this, is the load on it times the displacement of its center of gravity. The displacement of centroid of each sub-panel is 1/3 of the downward displacement of the panel center. The centroid here, the center of gravity, will go down 1/3 of this point. That is also obvious. So the work done internal is this, the moment along the hinge times its rotation, and this is the load on the structure times its displacement. And a table like this was set up, for example, for each design section. For each design section, like I have here, the moment positive and the moment negative is known, and depending on which way the hinge rotates, either the positive or negative moment will be applicable. And this shows the hinge lines, the moments either positive or negative, depending on which way the hinge rotates, and moment times rotation, and the sum of it gives the external work is the total load. This is the area, this is unit load, this is the displacement of the centroid centroid, and the internal work is here. Equated the two together and obtained the load capacity of the floor to be 0.6 kips per square foot. Now, before closing down, I'd like to review quickly another application. This is a constructed floor slab, reinforced concrete, and the load configuration and application was changed, and it was not clear whether the slab can resist it. We started by breaking the slab into strips. This is step number one. Redo the strip method and see whether the strip method based on the reinforcement shown on the drawings will give the results. The strip method did not give the acceptable solution. We went to redistribution of moments. That didn't work out well either. Then we went to the finite element step, break it into segment elements, obtain the solution, and included in the finite element solution the reinforcement as shown on the construction drawings. Now the software enables you to put the reinforcement in and determine the capacity, and if the capacity doesn't meet the demand, how much more you need. This is all done automatically. FEM analysis did not result in loads meeting the objective of the client. In the next was yield line. In the yield line analysis, again, we looked at the geometry, we looked at the reinforcement, and accounted for each bar that was shown on the drawing. Assumed a collapse mechanism in this direction. These are, by the way, depressions, not openings. Depressions for bathrooms. Now, hinge line here going down, hinge here up. This is one mechanism, and pulled it out so that we can calculate the rotations and displacements. The rotation of hinges, there are 9 hinges that do work internally, 1, 2, 3, and then 9 in total, obtained for each of the hinge lines the moment capacity based on the assumed displacement along here, and obtained from that moment capacity here the acceptable value. This is showing the internal and external work. The external work is area times unit capacity load times displacement. The external load is given by this formula for each of these segments. We have 6 of them, so there will be 6 terms, each relating to the area times displacement of its centroid. We just went through this external work, then worked the internal work, calculated the capacity to be so much. Then, to make sure that what we have assumed is valid, we looked at it differently and assumed a mechanism like what is shown here. Details of the mechanism are shown on the left. And for this mechanism, we obtained this capacity. This is larger than the value obtained for the hinge line of the other direction, so we assume that this 14.05 kilonewton per meter squared is the value to be considered for this floor. The solution is obviously upper bound. In theory, the location of the internal nodes, these are the internal nodes, and the similar location must be slightly moved to determine whether the change results to a smaller load capacity. This is for the validation, and then select the smallest capacity as final results. But the results from the hinge lines assumed by far exceeded the demand. As in this example, it may be practical to forego the additional analysis to determine the smallest value for capacity. It was considered that by moving these nodes a little bit around, the answer will be different, but the difference will not invalidate the conclusion. So, what did we cover? Talked about strip method as being the first step in evaluation of the capacity. If it doesn't work, we go to post-elastic response. Then we used the redistribution of moments, finite elements. Then came to yield line analysis, and load test I did not cover. I just mentioned that is the ultimate if the yield line doesn't work. I covered the example of intersection beams to illustrate the concept of yield line, then applied it to a propped cantilever, then went through hinge formation and yield line concept, talked about conservation of energy, external work being equal to internal work, talked about collapse mechanism examples, and calculation of the capacity at hinge line for non-prestressed and prestressed members. For prestressing, you really have to use a computer program. Then hinge line rotation evaluation. I gave you some triangular and quadrilateral segments, how the rotations are calculated. I really don't expect you to do that manually, but for background information was good to know how the software does it. Then talked about design validation, did the example of a bonded panel, then did the example of a column supported floor. Now the information that I presented to you was extracted from a chapter of this book on the right. Thank you for listening.